My name is Vladislav ALESHIN. I'm a senior researcher here in the Institute of Electronics, Microelectronics and Nanotechnology in Vilnius.
My name is Koen van ABEELE. I'm a professor at the University of Leuven at its campus in Kortrijk, Kulak. I'm a professor in applied mathematics and physics. So my research is actually on the edge of mathematics, physics and engineering. Yes. My research interest is in non-destructive testing of materials. That is actually to gather information about the status of a material without destroying it. Actually, what we want to do is we are looking for internal defects, and we want to detect those internal defects before they grow unconditionally and uncontrollably actually and cause major damage. There are many applications for non-destructive testing, and the most impressive one maybe is to look at damage in aircraft wings in order to prevent them from crashing. We are interested in our research in non-destructive testing techniques that are based on ultrasonics. Ultrasound is actually sound waves, but at a frequency that we cannot hear. Okay? So our interest is in nonlinear acoustics and in vibrothermography in order to characterize and detect defects such as delaminations. Vibrothermography is a technique that actually uses elastic waves in order to activate a damaged component and to generate harmonics of the frequency that we apply, and also frictional effects at the crack surfaces. Those frictional effects then generate heat and create a heat map actually of the delamination itself. You can actually compare it with the following observation. If you rub your hands against each other, you can feel actually the heat that is generated at the palm of your hands. In our technique, the rubbing of your hands against each other is actually what the elastic waves do, and the heat that is generated is due to the friction of the surfaces. In the project that Vlad and I have together, we are developing a 3D multiphysics, thermal, mechanic and acoustic finite element model in order to interpret and have a more detailed information about those thermal heat maps of the defects. We will apply those models also to optimize and to interpret actually the experimental results that we obtain. The model is a multiphysics model. It contains a mechanical part, a dynamical part, and a thermal part. The ultimate goal of our project is to develop a model and develop a technique also that allows us to quickly find and detect hidden defects and to assure the safety of the inspected components so that hazards can be eliminated.
How to extract some useful information on defects from signals that we measure. So what was typically used for many years, maybe for 30 or even 40 years, is this concept, is the concept of damage detection. Damage detection means that, for instance, in this case, we measure some damage indicators here. In this case, some harmonics appeared due to the presence of damage. And those indicators will tell us that somewhere in our sample there are defects, there is damage, and we don't know exactly where it is located, where it is coming from. And the next stage, which is also very well known, is the stage of imaging. Imaging is obtaining the distribution of damage indicators, exactly like it is shown here. So here there is some maximum, and we expect a crack to be here, somewhere in this zone. So using our modeling approach that allows to construct a link between the damage characteristics, damage geometry, size, orientation. So we are going to construct a link between damage parameters and measurable damage indicators. So one step forward would be to say that here in this region there is a crack of some certain size, of some certain orientation, and to extract in a more or less precise way the parameters of this crack. This is identification stage, and this is relatively new, and in that purpose we develop our modeling approaches. And there is one more step to go. The final concluding stage would be prognostics. Prognostics is when we add some methods of damage mechanics to our modeling approach, and then like that we're able to predict the future evolution of the damage. So we're not only able to identify where it is located, we can see its future evolution under certain conditions. And like that we will be able to answer the question if we have to replace this piece, this component of a construction, or it is still in the serviceable state. So it's very interesting for industrial applications because engineers want to know when they have to replace components or pieces of their equipment. So this would be a concluding prognostics stage of our research.